In the American West, a body of water holding 283 billion gallons is disappearing. Not slowly, not incrementally. It is vanishing at a scale that defies comprehension. Every single year, more than 115 billion gallons of its freshwater are lost. Gone, but not into a sinkhole, not into a sudden geological fissure. This is a story about a disappearance happening in plain sight, in the open air, and another happening deep in the silence of the earth. This is Utah Lake. And the mystery is not simply that its water is vanishing. The mystery is how many different ways it is vanishing at once. One way is an official managed event. Another way is a catastrophic industrial drainage. And the third is an invisible atmospheric process, so immense it could fill millions of classrooms with the water it takes in a single year. But here is the detail that tells the real story. In November of 1934, during the apex of the Dust Bowl, the lake did not just shrink. It ceased to exist. The vast basin, normally filled with miles of water, became a floor of cracked baked mud. Men, documented in local records, successfully walked from Pelican Point on the western shore, across the exposed lake bed, to the site of an old resort south of Lehi. For a brief, terrifying moment in history, Utah Lake was a desert, a memory. An event that proved that under the right conditions of extreme drought and heavy municipal demand, this colossal landmark could be erased from the map. That historical fact hangs over every subsequent conversation about the lake's water. It has happened before, and the pressures today are orders of magnitude greater. To understand what is happening now, you have to understand the lake's geometry. It is a geological anomaly, a remnant of the prehistoric Lake Bonneville, which 30,000 years ago covered a third of modern Utah. What remains is essentially a giant platter. Utah Lake spans 95,000 acres, an enormous surface area, but its average depth is a mere 9 feet. It is, for all intents and purposes, the largest, shallowest pan in the Intermountain West. When the relentless Utah sun and high desert winds beat down on that massive surface, the lake effectively becomes an evaporation engine. The result is the loss of 349,800 acre-feet of water every year, straight into the atmosphere. That is between 100 and 15 and 120 billion gallons annually. A volume of water that vanishes into thin air before it ever has a chance to flow downstream, nourish the wetlands, or reach the Great Salt Lake. This is the first and largest disappearance. A quiet, constant hemorrhage of freshwater into the sky. But the title of this investigation is specific. 45 billion gallons disappearing into the earth. That number is not an accident. And it does not refer to evaporation. That number points to a different kind of vanishing act, one that happened not by nature, but by design, and one that taps into the very same aquifers the region depends on. To find those 45 billion gallons, you have to look southeast of Utah Lake, into the Four Corners region, a landscape shared by Utah and Arizona. Beneath this land lies the Navajo Aquifer, a vast and ancient underground reservoir. For a period of 35 years, a single industrial operation, the Peabody Energy coal slurry pipeline, drilled into this aquifer. Its purpose was to transport pulverized coal from the Black Mesa mines. The medium it used was water, pristine, irreplaceable groundwater. When the mine finally ceased operations in 2005, the total volume of water it had permanently extracted from the earth was calculated. It was exactly 45 billion gallons. Gone, funneled out of the deep earth to move fossil fuels, never to return to the aquifer. It is a volume that is hard to visualize, but for perspective, the recent highly publicized demolition of the Copco and Iron Gate dams on the Klamath River drained 2 reservoirs totaling that exact same amount, 45 billion gallons. One engineered to restore a river, the other engineered to fuel a power plant. Both represent a profound and permanent alteration of the water landscape. It's a strange thing, a lake that can be drained by the sun, by industry, and by human command. Curious what you think about that power, and whether we're using it wisely. Now here is the part nobody is putting on the news. This pattern of disappearance is no longer just historical or industrial. It is now operational. It is a tool. Fast forward to the winter of 2024 and early 2025. The mountains ringing Utah Valley received a staggering, above-average snowpack. By February, Utah Lake was at 96.9% capacity. It was too full. Officials knew that when the spring melt began, the deluge of water would overwhelm the Jordan River. the lake's sole outlet, and cause catastrophic flooding in the densely populated Salt Lake Valley downstream. A decision had to be made. A proactive one. The Central Utah Water Conservancy District, under the direction of its general manager Gene Shawcroft, authorized an unprecedented release. They decided to make a portion of the lake disappear on purpose. The operation began on February 28, 2025. Jared Hansen, the project manager for the district, oversaw the opening of the control gates at the mouth of the Jordan River. A torrent of 500 million gallons of water a day began to flush out of Utah Lake. It was a controlled bleed. For weeks, the water cascaded north, a man-made river surge designed to create space to lower the lake and provide a buffer against the coming melt. In total, 23 billion gallons of water were intentionally drained from Utah Lake and sent into the desiccated basin of the Great Salt Lake. Gene Shawcroft stated it plainly. This is a way for us to be proactive for the spring runoff and do all we can to ensure water levels in Utah Lake and Great Salt Lake are healthy. It was an act of hydrologic triage, sacrificing billions of gallons from one lake to save a metropolis from flooding and to give a lifeline to another, terminally ill lake on the verge of ecological collapse. A disappearance by decree. This story, however, has a twist that no one saw coming. While engineers on the surface were busy moving billions of gallons of water around like pieces on a chessboard, a team of geophysicists was investigating a strange anomaly on the shores of the very lake they were trying to save. The Great Salt Lake, the final destination for Utah Lake's water, is a hypersaline, seemingly dead environment. Its shores are vast, dry salt flats, known as playas. But in one area, at Farmington Bay on the eastern edge, something was growing that shouldn't have been. Strange circular mounds of an invasive reed called Phragmites australis. These plants are notoriously thirsty and require immense amounts of fresh water to survive. Yet here they were, thriving on a cracked salty playa miles from any visible freshwater source. This was the clue. The reeds were drinking from something, and it was not the salty lake. Scientists from the University of Utah realized these mounds could only mean one thing. High-pressure freshwater was pushing its way up from deep, deep within the earth, punching through the saline clay and feeding the reeds from below. This is the part the headlines do not capture. To investigate this theory, a team led by Michael S. Zdanov, a distinguished professor of geology and geophysics, brought in technology that is essentially an MRI for the planet. In March of 2026, they flew a helicopter back and forth over the Farmington Bay Playa. Suspended beneath it was a massive electromagnetic hoop, 50 feet in diameter. This device shot powerful electrical currents thousands of feet into the ground. By measuring the resistance of the Earth to these currents, the scientists could create a 3D map of what lay beneath. Salt water is highly conductive and offers little resistance. Freshwater, by contrast, is highly resistive. The data that came back was staggering. It was the confirmation of a geological miracle. Beneath the hypersaline crust of the Great Salt Lake, the surveys revealed a massive, previously unknown freshwater system. Not a small pocket. Not a shallow aquifer. It was a vast reservoir of freshwater saturating the sediments, extending downward to a depth of 10,000, then 12,000, then in some places, 13,000 feet. That is nearly 4 kilometers, 2.5 miles straight down. A hidden ocean of freshwater, trapped under immense pressure, sealed beneath a terminal saltwater lake. As Professor Zdanov explained, we were able to answer the question of how deep this potential reservoir is, and what its spatial extent is. If you know how deep, you know how wide. You know the porous space, you can calculate the potential freshwater volume. The Phragmites reeds were not an anomaly. They were messengers, living proof of a colossal underground water system that no one knew existed. Finding a hidden freshwater sea 13,000 feet down, that's the kind of discovery we live for on this channel. If you feel the same, subscribing is the best way to make sure you see the next one. This discovery completely reframes the entire story of water in the Great Basin. While humanity frets about the disappearing water on the surface, an immense volume has been sitting here, silently, for millennia. It is a mind-bending paradox. Utah Lake loses 120 billion gallons a year into the sky. The Navajo Aquifer lost 45 billion gallons into an industrial pipeline. The Central Utah Water Conservancy District intentionally drained 23 billion gallons to prevent a flood. All of these are disappearances, subtractions from a finite surface supply. And yet, simultaneously, miles beneath the salt flats, an unquantified volume of freshwater is actively pushing its way upward toward a world that is desperately seeking it. The history of Utah Lake itself is a story of ecological transformation, much of it tragic. When U.S. Army Captain John W. Gunnison first surveyed the lake in the 1850s, he described a vibrant ecosystem with lush marshlands and clear water thick with native vegetation. He documented the native tribe's name for it, Timpanogos, reflecting the people who lived by its shores. The lake teemed with a unique species of fish, the June sucker Chasmistes leoris, found nowhere else on Earth. But this pristine state would not last. By the 1880s, commercial fishing had decimated the native trout populations. In a decision that would have catastrophic, century-long consequences, state officials introduced a hardier, more resilient species to replace them: the common carp, Cyprinus carpio. The carp were a disaster. As bottom feeders, they churned up the lake bed, uprooting the vast underwater forests of aquatic plants that held the sediment in place and kept the water clear. The water turned murky, a condition that persists to this day. The sunlight could no longer penetrate to the bottom, and the remaining native vegetation died off. The ecosystem collapsed, favoring the invasive carp and pushing the native Junesucker to the brink of extinction. For decades, the Utah Division of Wildlife Resources, or DWR, has been engaged in a massive, multi-million-dollar effort to remove carp and restore the lake's habitat to save the Junesucker, a fish that is a living link to the lake's original, pre-development state. The lake we see today, turbid, shallow, and ecologically stressed, is a direct product of that 19th century decision. Its vulnerability to evaporation is amplified by the ecological damage it has sustained. Without the anchoring vegetation, the wind and waves have a greater effect, churning the shallow water and increasing its exposure to the air, which in turn accelerates the rate at which those 120 billion gallons vanish each year. This story is so much deeper than just one lake. If you think more people should understand the complex pressures on water in the West, sending this video to someone who cares about this stuff actually helps. These systems are all connected, from the sky to the deep earth. The different disappearances are not isolated events. They are interconnected parts of a regional system under extreme duress. The 45 billion gallons pumped from the Navajo Aquifer represents a permanent loss of groundwater storage. That matters because groundwater and surface water are often linked. Depleting an aquifer can reduce the flow of springs and streams that feed surface lakes and rivers, creating a domino effect. To put that 45 billion gallons into an even more startling context, consider this. Globally, it is estimated that the world's cattle population consumes that same volume of water every single day. The scale of water consumption for agriculture and industry is a planetary force. The Peabody Mine's withdrawal was a 35-year-long drain, a slow but terminal bleed from a finite resource. Then there is the engineered disappearance of February 2025. This act, while necessary for flood control, highlights the impossible choices water managers in the West now face. They are caught between the dangers of too much water in one place, snowpack, and not enough in another, the Great Salt Lake. The 23 billion gallons sent down the Jordan River was not a loss to the system, but a transfer from a healthy freshwater lake into a dying terminal lake. This was a calculated choice to use a surplus to address a deficit, a sign of a water management system that is no longer passive, but actively and frantically redistributing resources to stave off collapse on multiple fronts. It is a far cry from the accidental disappearances of the past. And then there is the existential question buried in the data from Michael Zdonov's geophysics team. If a colossal freshwater reservoir exists 13,000 feet beneath the Earth, what does that mean for the surface world's water crisis? Is it a potential resource? A lifeline in waiting? The answer is complex. The pressure required to keep that water trapped for millennia is immense. Accessing it would require technology and energy expenditures that are currently unimaginable. Furthermore, no one knows the recharge rate. Is it a fossil aquifer, a finite deposit of ancient water, or is it being actively replenished? Pumping it could have unforeseen geological consequences, such as land subsidence or triggering seismic activity. The discovery is scientifically profound, but it is not a simple solution. It is a new, massive variable in an already complex equation. It proves that our understanding of the planet's hydrology is incomplete. We have been staring at the ceiling, worried about a leak, while an ocean churns silently in the basement. The contrast between the known and the unknown is stark. On the one hand, we have the meticulously documented disappearance of Utah Lake in 1934. The images of men walking on the dry bed are a tangible warning. We have the precise accounting of the 45 billion gallons pumped by Peabody Energy, a story of industrial consumption with a clear beginning and end. We have the daily logs from the CUWCD in 2025, tracking every cubic foot of the 23 billion gallons they released down the Jordan River. These are known quantities. The disappearances are frightening, but they are measurable. But the atmospheric disappearance is different. 120 billion gallons a year is a calculation, an estimate based on variables like temperature, wind, and humidity. It is an invisible, ongoing event that happens molecule by molecule over 95,000 acres. You cannot photograph it like a dry lake bed. You cannot chart it like a pipeline's output. It is a force of nature amplified by the lake's unnatural state. And the newly discovered deep earth reservoir is the greatest unknown of all. Its existence hints at geological processes and water cycles that operate on a timescale far beyond human experience. It forces us to ask what else we are missing. What other systems are operating unseen beneath our feet? The story of Utah Lake is the story of the modern American West in miniature. It is a wrestling match between natural cycles and human interventions. It is a place of immense natural beauty that has been profoundly altered by human error. It is a resource that is being depleted by forces both visible and invisible, both natural and industrial. And now, it is the site of a discovery that could rewrite our understanding of how water is stored on this planet. Each disappearance, the evaporation into the sky, the pumping from the ground, the controlled release down the river, is a chapter in a much larger narrative about scarcity, survival, and the shocking resilience of nature. For now, the systems remain in motion. The sun and wind will continue to pull their share from Utah Lake's shallow surface. The legacy of the Navajo Aquifer's depletion will ripple through the region for generations. And water managers like Gene Shawcroft will continue to make difficult, pragmatic choices, moving water from where it is abundant to where it is desperately needed, all under the shadow of a changing climate. The discovery at Farmington Bay does not solve these problems. It adds a profound, humbling layer of complexity. It reminds us that the Earth holds secrets far deeper than we imagined. So, 3 questions hang over the Great Basin tonight. How much fresh water is truly locked away in these deep Earth reservoirs beneath the West? As the surface world gets hotter and drier, what happens when the pressures of a thirsty civilization collide with the immense geological forces that have kept this water hidden for eons? And which is vanishing faster, the water we can see, or our time to understand and protect it? The water cycle here is now a fractured hybrid thing.